Okay, we're going to continue our exploration of different material properties and move on to chapter 6, which is on mechanical properties in particular. Chapter 5 in the book that we just finished was on how some properties depend on temperature, and we had looked at diffusion with some careful detail there. As usual, we're continuing our quest for intrinsic properties. In other words, properties that don't depend on how much of it we have. So keep that in mind as we try to understand what we're trying to introduce today. So consider a very common mechanical property, which is the force needed to break something. And imagine that I want to break this black rectangle of material by pulling it on the two ends. Now, the force to break something is not intrinsic. That's an extrinsic property because it depends on what cross-sectional area you have. For example, the blue item would be easier to break than the black one. So the blue rectangle is the same length, but a smaller cross-sectional area. So to break the blue one, I have fewer bonds that need to be broken. To break the black one, I have to break more atomic bonds. I kind of imagine each of these dots as an atom on the crystal here. So to break the blue rectangle, I simply have fewer atomic bonds that have to be broken. Okay, so we need a new property, something that captures the force per atomic bond, not the total amount of force. I'm trying to find some kind of intrinsic property that captures the force needed to break something. So what we want is force per atomic bond. And instead of trying to capture that directly, we will instead introduce a property which is the force per cross-sectional area. So it's the force per the amount of area shaded there, which we'll call the stress. And our symbol for stress will be a Greek letter S, which is a sigma. Now, right off the bat, you can see what the units of stress would have to be. It would have to be the units of force, which is newtons, divided by the units of area, which is square meters. And that combination of a newton per square meter is also called a Pascal. Excuse me. So stress is going to be measured in pascals. Okay, next property. And this is not so much a property, but another parameter to introduce, which will be relevant, is how much something is stretched. So how much has the object been stretched? Now here you could report it in terms of meters. So if you have two beams, one longer than the other, everything else is the same. If you apply the same force to these two beams, the longer one is going to stretch roughly twice as much. So that's for the same force, same cross-sectional area, same stress. Note, remember, stress is force per area. So the amount that something's been stretched, as in like change in length, that would be an extrinsic variable. It depends on how long the sample is. So we're going to introduce a new way of describing how much something has been stretched, which is the change in length per length of the object. This parameter does not depend on how long the object is. I know it kind of looks like it does because it's got the length in it, but the whole point of that length was to cancel out the effect that longer objects tend to stretch more. This parameter, change in length over length, we will call strain, which we will have the symbol, the Greek letter epsilon for that. You can see the units of strain would be no units. And think of this as like the amount of stretch per atomic bond. It's how much each bond has gotten stretched. And that's more of an intrinsic property than an extrinsic property.